Hello listeners, today we embark on a journey that measures not only infinite space, but also attempts to penetrate the mysteries of infinite time. This journey is based on the great book whose author gave us the courage to understand the universe's biggest secrets, Stephen Hawking's A Brief History of Time. This is the story of human curiosity spanning centuries. We are trying to understand who we are, where we came from, and what our place is in this vast timeless universe. Hawking begins with a striking anecdote. A famous scientist, whom some people suggest was Bertrand Russell, was giving a lecture on astronomy. He explained that our Earth revolves around the Sun, and our Sun also revolves within a large galaxy composed of many stars. After the lecture, an old woman stood up and said, "Sir, everything you have told us is wrong. The world is actually a large flat plate resting on the back of a giant turtle." The scientist smiled and, trying to make a clever point, asked, "And what is that turtle standing on?" The old woman replied with a triumphant smirk, "You're very clever, my child, but below it's just turtles all the way down." This story leads us to the profound intellectual struggle that has persisted through the ages. Folk belief versus scientific truth. We are forced to ask why we believe our current understanding that the Earth is round and orbits the Sun is more correct than the concept of an infinite series of turtles. This question is about philosophy and the basis on which we establish the truth of our beliefs. Everything we know about the universe, its origin, its destiny, and its fundamental nature, is an attempt to create a mental model or picture. It is our picture of the universe that gives us the courage to wrestle with the fundamental questions of existence. Did the universe have a beginning? If so, what was before that? What is time? Will it ever stop? Can we go back to the past? These questions, once belonging strictly to the domain of religion and metaphysics, are now coming closer to answers, thanks to new scientific discoveries. Our intellectual journey begins around 340 BC with the Greek philosopher Aristotle. In his book On the Heavens, Aristotle challenged the popular notion of a flat Earth. He presented two major proofs that the Earth is a sphere, not flat. The lunar eclipse proof. During a lunar eclipse, the Earth passes between the Sun and the Moon, and the shadow cast by the Earth on the Moon is always round. The North Star proof. When the Greeks travelled south, the North Star appeared lower in the sky. This difference is only possible if one is traversing a curved surface. Aristotle estimated the size of the Earth, a figure that was roughly double the accurate figure known today. A third observational proof was that when a ship approached from a distance, its sails appeared first, followed gradually by the whole ship. Aristotle, however, assumed that the Earth was stationary, and the Sun, Moon, and planets revolved around it. Ptolemy further developed this model in the 2nd century AD. In his model, the Earth was at the centre, surrounded by 8 spherical shells containing the heavenly bodies. The Christian Church adopted this model because it allowed for a place for heaven and hell. The Earth-centered model was finally challenged in 1504 when Nicholas Copernicus proposed a new model in which the Sun was at the centre and the planets revolved around it. He circulated this idea anonymously at first, fearing the Church. The revolution gained strength in 1609 when Galileo Galilei used his telescope to observe small moons revolving around Jupiter. This proved that not everything revolved around the Earth. Simultaneously, Johannes Kepler modified the circular orbits to elliptical orbits, which matched observations. This intellectual progress reached its pinnacle in 1687 with the key publication of Isaac Newton's Principia Mathematica, which is considered one of the most important books in science. Newton established the laws of motion and gave us the law of universal gravitation. He showed that every object attracts every other object, and this force keeps the Moon in orbit around the Earth and the planets in orbit around the Sun. With this new understanding, the idea of stars being distant suns became popular. However, Newton faced a grave difficulty. If the universe was infinite, and all the stars were attracting one another, why did the universe not collapse into a single point? He suggested that if the stars were infinite, the gravitational forces would balance out. Today we know that this static solution was unstable. Because gravity is always attractive, a stable, infinite universe is impossible. The universe must either be expanding or contracting. A major objection to the idea of a static and infinite universe was posed by the German philosopher Heinrich Olbers in 1823. This is known as Olbers' paradox. The problem was, if the universe were infinite and static, The entire night sky should appear as bright as the surface of the sun. Olbers suggested that the light from distant stars was absorbed by dust and gas, but that matter would eventually heat up and glow as brightly as the stars. The only logical resolution to this paradox is that either the stars began shining only a finite time ago, or the light from them has not yet had time to reach us. This pointed directly to the question of the universe's beginning. Christian thinker St. Augustine argued that human civilization is progressing, and if it were infinitely old, we would recall all major inventions. He estimated creation at around 5000 BC. Immanuel Kant discussed this deeply in 1781 in his Critique of Pure Reason. The arguments for and against a beginning were equally strong, but St. Augustine argued that the meaning of time only exists when the universe exists. Time began with the universe. The concept of an eternally unchanging universe changed forever in 1929, when Edwin Hubble made the great discovery that galaxies are moving away from us. The universe is expanding. This meant that if we trace time backward, the entire universe must have been concentrated in a single place, with infinite density. This is the basis of the Big Bang theory. At this moment of the Big Bang, the universe was infinitely small and dense, and all physical laws fail. Any event that occurred before the Big Bang would have no influence on the present universe. This means the definition of time did not exist before the Big Bang. Time began with the Big Bang itself. Our modern understanding of motion and the forces that govern it is the bedrock of physics, yet this foundation was not built easily. For centuries, the world relied on the intuitive, though ultimately incorrect, principles laid down by Aristotle. His philosophy held that an object naturally tended toward a state of rest and would only move if an external force were continually acting upon it. This view had profound consequences for how people perceived falling objects. Aristotle believed that heavier objects would fall faster than lighter ones, because the Earth's pull on them would be greater. Furthermore, Aristotle and his followers believed that the laws of the universe could be understood entirely through pure thought and deduction, without the need for experiments. Consequently, for nearly 2,000 years, no one bothered to seriously test whether objects of different weights actually fell at different speeds. They assumed this was a matter of pure thought. The revolution began with Galileo Galilei. Galileo recognized that the true path to understanding nature lay not in philosophical contemplation, but in systematic observation and measurement. While the famous story suggests Galileo dropped objects from the Leaning Tower of Pisa, the reality of his method was more insightful. Galileo used smooth, inclined slopes to roll balls of different weights. This technique allowed him to study the effect of gravity on objects, but by slowing the process down, it made accurate measurement of the speed and acceleration much easier. His experiments yielded a result that directly contradicted Aristotle. Objects of different weights accelerate at the same rate. He showed that a ball rolling down a slope increases its speed every second, regardless of whether the ball is light or heavy. The only reason a feather and a heavy weight fall differently in the atmosphere is due to air resistance. This was spectacularly demonstrated by astronaut David R. Scott during the Apollo 15 mission on the Moon, which has no air. He dropped a feather and a heavy weight simultaneously, and they both hit the lunar surface at the exact same moment. Galileo's work paved the way for Isaac Newton, who took these experimental findings and formalized them into the elegant and enduring laws of motion. Newton proved that the true function of a force is not merely to cause motion, as Aristotle thought, but to change an object's speed, that is, to cause acceleration. Newton published his laws in 1687 in the Principia Mathematica. Newton's first law: if no force acts on a body, it will always move at a constant speed in a straight line. This directly refutes Aristotle's idea that an object requires a continuous force to keep moving. Newton's second law: when a force acts on a body, it causes that body to accelerate. This acceleration is proportional to the force and inversely proportional to the mass. A more powerful engine, more force, generates greater acceleration, but a heavier object, more mass, experiences less acceleration for the same force. Newton then unified these laws with his law of universal gravitation, which states that the gravitational attractive force between two objects is proportional to the product of their masses. This final synthesis explains Galileo's finding. A heavier body experiences a greater gravitational force, but it also has more mass. According to Newton's second law, these two factors cancel each other out, resulting in the same acceleration for all bodies, regardless of weight. Furthermore, Newton showed that gravitational force decreases with the square of the distance. This specific mathematical relationship is why planets follow elliptical orbits. The consequence of Newton's laws extended beyond mere motion. They fundamentally altered the understanding of our place in the cosmos by rejecting Aristotle's idea of a preferred state of rest. Aristotle, rooted in his geocentric model, believed that the Earth was the centre of rest, with everything else in motion around it. Newton's laws, however, revealed that there is no absolute state of rest. Motion is relative. Consider a train moving at a high speed. We can describe this motion in two equivalent ways. The train is moving while the Earth is at rest, or the Earth is moving while the train is at rest. There is no experiment performed inside the train that can determine whether it is moving or at rest in an absolute sense. For example, if someone plays ping pong inside the moving train, the ball will behave exactly as it would on a table fixed to the ground. This principle, that motion is relative, means that the absolute position of an event cannot be determined. If an observer on the track watches a ball fall straight down inside the train, they will see the ball describe an arc because the train is moving. The perceived position of the event, the ball falling, is different for different observers. Newton was troubled by this conclusion, which it conflicted with his belief in an absolute God. Philosophers, however, accepted the idea of relative motion, but they held firm to the other Newtonian absolute, time. It was common sense to believe that time was an absolute quantity that would yield the same measurement for any observer, regardless of their motion. The notion that space and time are entirely separate quantities seemed correct. This deeply held belief in absolute time and space was shattered by the advent of electromagnetism and the speed of light. As demonstrated by the Danish astronomer Ole Rømer in 1676, light travels at a fixed finite speed. Rømer observed that the eclipses of Jupiter's moons did not occur at perfectly regular intervals. When the Earth was moving away from Jupiter, the light took longer to reach Earth. Rømer estimated the speed of light to be about 140,000 miles per second. Then in the 19th century, James Clerk Maxwell developed his theory of electromagnetism. Maxwell's equations predicted that light was an electromagnetic wave travelling at a fixed speed. This fixed speed posed a contradiction to the Newtonian view of relative motion. Relative to what was this speed fixed, especially since Newton had eliminated absolute rest? To solve this, scientists hypothesized the existence of the luminiferous ether, an invisible medium through which light waves travelled. If the ether existed, the speed of light should vary depending on the observer's motion relative to the ether. The famous Michelson-Morley experiment in 1887 was designed to detect this variation. They measured the speed of light in different directions relative to the Earth's motion. The result was astonishing and completely unexpected. The speed of light was exactly the same in both directions. The ether did not exist. Albert Einstein, working in 1905, finally provided the revolutionary theoretical framework to make sense of this fact. He proposed that the ether was unnecessary. We simply needed to discard the common-sense notion of absolute time. His special theory of relativity was based on the premise that the laws of science, including the speed of light, must be the same for all freely moving observers. The consequence was radical. Because all observers must agree on the fixed speed of light, they must disagree on the time elapsed. Time is relative, and each observer has their own personal timescale. Einstein showed that space and time are not independent, but are fused into a single four-dimensional continuum, space-time. An event is defined by 4 coordinates, 3 for space and 1 for time. This unified structure fundamentally changed our understanding of the universe, proving that the separation between space and time, which seemed like common sense for centuries, was false. The great question left unresolved by special relativity in 1905 was how to incorporate gravity. Newton's theory described gravity as an instantaneous force acting across vast distances. If the sun suddenly vanished, Newton's theory suggested the Earth would immediately fly off into space. This conflicted directly with the core principle of relativity, which stated that nothing can travel faster than the speed of light. Any change in gravity should take time to propagate across space, just like light. Between 1908 and 1914, Albert Einstein wrestled with this profound contradiction, seeking a way to make gravity compatible with the speed limit of the universe. In 1915, he finally proposed a revolutionary idea that changed our understanding of the cosmos, the general theory of relativity. Einstein's insight was that gravity is not a force in the traditional sense, but an effect of the curvature of space-time caused by the mass and energy within it. He proposed that massive objects like the Sun cause the fabric of space-time to warp or curve, much like a bowling ball placed on a stretched rubber sheet. Objects moving near a mass are simply following the straightest possible path, called a geodesic, in this curved space-time. The Earth does not orbit the Sun because the Sun exerts an invisible force on it. It orbits because the Earth is following the natural curve of space-time created by the Sun's enormous mass. General relativity made predictions that differed subtly from Newton's laws, particularly in strong gravitational fields. Mercury's orbit, Newton's theory could not fully explain the small rotation, precession, in the elliptical orbit of the planet Mercury. Einstein's theory, based on the curvature of space-time, provided the exact correct prediction for this deviation. Bending of light. Since light travels through space-time, it should also be affected by the curvature created by mass. Gravity should bend the path of light. This was dramatically confirmed in 1919, when a British expedition observed a solar eclipse. The expedition proved that light from distant stars passing near the Sun was indeed bent, making the stars appear in a slightly shifted position. This provided powerful evidence for Einstein's theory. Time dilation. General relativity predicted that time runs slower in the presence of strong gravity. The more massive the object, the slower time flows near it. This was experimentally verified in 1962 using accurate clocks. The clocks in the stronger gravitational field ran slower, exactly matching Einstein's predictions. Even today, this effect must be accounted for by the GPS satellites to ensure accurate navigation. The greatest philosophical consequence of general relativity was the realization that space and time are not just a fixed, passive backdrop upon which events occur. Instead, they are dynamic entities that are affected by, and in turn, affect the matter and energy within the universe. When a body moves, the curvature of space-time changes. Space and time are active participants in the universe's motion. This fundamentally dynamic view of space-time ultimately led to the demise of the idea of a static, unchanging universe. The universe must either be expanding or contracting. This provided the crucial theoretical framework that led to the Big Bang Theory and the understanding of the universe's beginning and possible end. The search for our place in the cosmos has always been limited by what we can see. On a dark night, the visible stars appear scattered, but they are concentrated in a band of light we call the Milky Way. By 1750, some astronomers suggested that the Milky Way was a disc-shaped system. Sir William Herschel later confirmed this, solidifying the view that our spiral galaxy was a large rotating collection of stars. For centuries until the early 1924, it was widely believed that the Milky Way was the entire universe. The true scale of the cosmos was revealed by Edwin Hubble. In the 1920s, Hubble proved that the fuzzy patches of light previously considered gas clouds were, in fact, vast separate galaxies located far outside our own. To prove this, he had to determine the immense distances to these objects, using indirect methods based on their brightness. Hubble's work revealed that our galaxy is only one of hundreds of billions of galaxies that can be seen with modern telescopes. Each of these galaxies, in turn, contains billions of stars. Our Milky Way is about 100,000 light-years wide and rotates slowly. The light coming from these distant objects holds the key to the universe's history. When starlight is passed through a prism, it separates into a spectrum of colours. The spectrum is marked by missing colours, dark lines that correspond to the specific wavelengths absorbed by the chemical elements in the star's atmosphere. In the 1920s, when Hubble examined the spectra from these newly discovered galaxies, he found a crucial, consistent feature. The characteristic patterns of missing colours were shifted toward the red end of the spectrum. This phenomenon is explained by the Doppler effect. Just as the pitch of a car engine sounds lower as it moves away from you, the wavelength of light is stretched if the source is moving away. This stretching causes the light to shift toward the red end of the spectrum, known as redshift. A shift toward the blue end, blue shift, occurs if the object is moving closer. Since almost all galaxies showed a redshift, Hubble concluded that almost all other galaxies are moving away from us. In 1929, Hubble made an even more dramatic discovery. The farther away a galaxy was, the faster it was moving away. This relationship proved an inescapable fact. The universe is not static, it is expanding. This discovery finally settled the philosophical debate that had troubled scientists from Newton to Einstein. If the universe is expanding, it means that if we trace the expansion backward, all the matter in the universe must have been packed into a single point in the finite past. This moment is the beginning of the universe, now known as the Big Bang. The discovery that the universe is expanding, proven by Edwin Hubble in 1929, resolved a centuries-old philosophical debate, shifting the question of the universe's origin from pure metaphysics to the realm of science. The universe's dynamic nature meant that if we trace its history backward, all matter must have been concentrated into a single, infinitely dense point, the Big Bang. The only physicist to seriously explore the consequences of general relativity for a dynamic universe was the Russian scientist Alexander Friedmann. He assumed the universe was uniform, looking the same in every direction, and homogeneous, looking the same from every place. Based solely on these assumptions, Friedmann mathematically proved in 1922 that the universe could not be static. It must either expand or contract. His prediction preceded Hubble's observational proof by several years. Friedmann's equations produced three possible models for the universe's eventual fate. One model was the closed universe, where if the expansion was slow enough, gravity would eventually halt the expansion and pull everything back into a final big crunch. This could be a cyclical model, repeating the Big Bang and Big Crunch. The second was the open universe, where if the expansion were fast enough, gravity would never be able to stop it, and the universe would expand forever. The third was the critical universe, where the expansion rate was perfectly balanced, slowing down but never truly stopping. The discovery that finally proved the Big Bang model correct came unexpectedly in 1965. At Bell Telephone Laboratories in New Jersey, two scientists, Arno Penzias and Robert Wilson, were testing a sensitive microwave detector. They kept finding an unwanted, persistent noise in their instrument. This noise was uniform in every direction and constant, ruling out atmospheric effects, instrument faults, or even, as they once checked, bird droppings. This noise was the cosmic microwave background CMB radiation, the faint leftover heat signature of the Big Bang. At the same time, physicists at Princeton, based on earlier work by George Gamow, had theorized that the early universe was so hot and dense that it would have glowed white hot. They predicted that this ancient glow would still be detectable today, highly redshifted into the microwave region due to the universe's expansion. Penzias and Wilson had accidentally found this cosmic echo. The CMB provided strong evidence that the universe evolved from an incredibly hot, dense state. The CMB's temperature is virtually the same in every direction, providing powerful support for Friedmann's assumption that the universe is uniform on large scales. The discovery of the CMB was a powerful refutation of the competing steady-state theory, proving that the universe was once very dense, meaning it could not have been static. If every galaxy is moving away from us, a simple interpretation might suggest we are at the center of the expansion. However, Friedmann's model resolves this. Imagine spots on the surface of a balloon. As the balloon is inflated, every spot moves away from every other spot. Every spot sees every other spot receding, yet there is no single center of the expansion. The universe is expanding and every point is equivalent. Friedmann's model, confirmed by observation, implied that the universe originated from a point in the finite past where all matter was compressed together. This point is a singularity, where the density and curvature of space-time are infinite. At this extreme point, the equations of general relativity break down, and the laws of physics cease to apply. For science, the singularity of the Big Bang defines the beginning of time. Any event that might have occurred before the Big Bang would have no influence on the present universe, meaning its existence is meaningless to our current understanding. The idea of the Big Bang singularity faced initial resistance, particularly from those who preferred a predictable, elegant universe, or those who held to strict determinism. The singularity implied that the universe was unpredictable at its origin. Some Russian scientists tried to show that the Big Bang was merely a limitation of Friedmann's models, arguing that the universe might have been contracting, with particles passing close by each other, before beginning to expand, thus avoiding the singular point. However, the final inescapable proof came from the work on singularities. Building on the work of Roger Penrose regarding the collapse of stars into black holes, Stephen Hawking realized that by reversing time, Penrose's theorem must also apply to the expanding universe. Penrose's theorem stated that a collapsing region must end in a singularity. Hawking showed that an expanding universe must have begun with a singularity, provided general relativity is correct. In 1970, Hawking and Penrose published a joint paper proving that according to general relativity, the universe must have begun with a singularity, the Big Bang. This proof meant that time and space had a definite beginning. The existence of the singularity presents a crisis for physics. Because all the laws fail at that point, general relativity is an incomplete theory. It cannot tell us how the universe started. If physics breaks down, we cannot predict the past. This realization forced scientists to look for a new theory, one that could describe the universe at the extreme conditions of the singularity. That theory must necessarily combine general relativity, which describes the large scale, with quantum mechanics, which describes the micro scale. The singularity occurs in a region where quantum effects are extremely important, meaning the search for a quantum theory of gravity is the key to understanding the true nature of the universe's origin. This quest moves physics beyond the simple breakdown point and toward the grand, unified description of reality. The classical vision of the universe, rooted in Newton's laws, was one of strict determinism. The French scientist Marquis de Laplace formalized this idea, claiming that if we knew the exact position and speed of every particle in the universe at one moment, we could predict its entire future. This deterministic view suggested that every event, including human behavior, followed fixed, predictable rules. This belief held sway until the early 20th century, when the development of quantum physics shattered the idea of a completely predictable universe. The first hint of the failure of classical physics came from the study of heat radiation. Scientists realized that if a hot object radiated energy equally at every frequency, the total energy radiated would be infinite, which is physically impossible. In 1900, Max Planck offered a radical solution. Light and energy are not emitted continuously, but in small discrete packets called quanta. Higher frequency packets carry more energy, which limited the total emission and solved the infinity problem. The full impact of this quantum idea on determinism became clear in 1926, when Werner Heisenberg demonstrated a fundamental limitation in our ability to observe the universe. Heisenberg's uncertainty principle stated that there is an inherent fundamental limit to how accurately one can simultaneously measure both the position and the velocity of a particle. To measure a particle's position accurately, you need light with a short wavelength, but the light's energy will disturb the particle and change its velocity. Conversely, using a long wavelength to keep the velocity accurate makes the position uncertain. This principle meant that Laplace's vision of perfect prediction was impossible. If we cannot know the present state of the universe with perfect accuracy, we cannot predict its future with perfect accuracy. The uncertainty principle meant that particles no longer had a well-defined position and velocity. Instead, they exist in a quantum state which is a combination of both. Quantum mechanics, therefore, does not give a single definite result for an experiment, but rather multiple possible results, each with a specific probability. You can repeat the experiment many times, and each result will occur a certain percentage of the time, but you cannot know the exact outcome of a single event beforehand. Albert Einstein, despite his contributions to quantum mechanics, refused to accept this inherent unpredictability, famously saying God does not play dice with the universe. Yet experiments have repeatedly shown that quantum mechanics is correct, and randomness is a fundamental part of reality. Today, quantum mechanics is the foundation of modern technology, including computers, electronics, and even biology. Quantum mechanics reveals a universe far stranger than the classical models described by Newton. One of the most counterintuitive properties is wave-particle duality. Light, which we traditionally think of as a wave, can behave like particles, photons, and particles of matter, like electrons, can behave like waves. A famous experiment that demonstrates this is the two-slit experiment. If light is shone through a partition with two small slits, an interference pattern forms on a screen, which is characteristic of waves. If this same experiment is done with electrons, which are solid particles, the same wave pattern appears. This suggests that a single electron is travelling through both slits simultaneously, behaving like a wave. This proves that at the quantum level, reality breaks our everyday logic. This wave nature also provided the correct explanation for the stability of atoms. Previously, the early model of the atom suggested electrons orbited the nucleus like a tiny solar system. However, classical physics predicted that these electrons should quickly lose energy and spiral into the nucleus, causing the atom to collapse. Niels Bohr in 1913 proposed that electrons could only exist in fixed, quantized orbits. Quantum mechanics explained why. Electrons are waves. An electron can only exist in an orbit where its wave perfectly fits, meaning the circumference of the orbit is a whole number, multiple of the electron's wavelength. If the wave doesn't fit, it interferes with itself and cancels out, making the orbit unstable. Quantum mechanics is extremely successful in explaining the microscopic world. However, it faces a major conflict when confronted with general relativity, which describes the large-scale universe. The conflict is apparent in extreme environments, like the Big Bang or black holes, where gravity is incredibly strong. General relativity, without quantum effects, predicts infinite density at these points, which is physically meaningless. Since both theories cannot be simultaneously correct under these conditions, a complete theory must unify them. The search for a quantum theory of gravity is therefore the ultimate pursuit in physics. It is the only way to find a single set of laws that describes all phenomena, from the smallest particle to the largest structures in the cosmos. Without it, we cannot understand the true nature of the universe's beginning or its final destiny. I will continue the script, providing the next two sections, Part 11 and Part 12, in the requested slow-paced, philosophical narrative style, ensuring all numbers and years are written out in English form, and the content remains simplified for easy AI voice reading and general audience comprehension. The journey to understand the expanding universe was not a straightforward path of discovery, but one marked by profound resistance to the dynamic nature of gravity. After Newton established his law of universal gravitation in 1687, it was clear that an infinite static universe was inherently unstable. Gravity, being an attractive force, would inevitably cause a collection of stars to collapse inward toward a single point. Yet, the belief that the universe was static, unchanging, and existing eternally in its current state was so deeply ingrained that even the greatest minds sought to defy the logical conclusion of their own theories. Prior to the 20th century, most people held to one of two beliefs. Either the universe had always existed in its current state, or it had been created in a single moment by a divine force. The idea that the universe could expand or contract was simply not contemplated. Instead of accepting the inevitable collapse predicted by their own laws, scientists attempted to modify gravity itself. They suggested that at very long distances, gravity might become repulsive, pushing stars apart rather than pulling them together, thereby maintaining a perfect balance. However, this balance model would be unstable. If some stars moved even slightly closer to each other, the attractive force would dominate, and they would continue to collapse inward. If they moved slightly farther apart, the repulsive force would win, and they would rush away from each other. The universe would either rapidly collapse or fly apart. This resistance to the dynamic universe reached its peak with Albert Einstein. When Einstein formulated the general theory of relativity in 1915, the theory itself naturally suggested a dynamic cosmos, one that must either be expanding or contracting. Yet Einstein, sharing the static bias of his time, initially found the idea of a moving universe disturbing. To reconcile his revolutionary theory with the prevailing belief in a static cosmos, Einstein performed an extraordinary yet ultimately flawed intellectual maneuver. He introduced a new mathematical term into his equations. This term was the cosmological constant. The cosmological constant was an artificial force designed to work in opposition to gravity. It was a repulsive energy inherent in the fabric of space-time itself, existing independently of any matter. It was precisely designed to exactly balance the attractive force of gravity, thus holding the universe in a state of perfect static equilibrium. The only physicist to take the original dynamic implications of general relativity seriously was the Russian scientist Alexander Friedmann. While Einstein and others were trying to force a static solution, Friedmann was exploring the possibility of an expanding universe. Based on two simple assumptions, that the universe looks the same in every direction, and that it looks the same from every place, Friedmann demonstrated mathematically in 1922 that the universe could not be static. It must either expand or contract. He predicted the expansion of the universe years before it was observed. The ultimate irony came in 1929 with the observational confirmation of cosmic expansion by Edwin Hubble. Hubble's discovery that galaxies are moving away from us proved that the universe was not static, the universe was expanding. Faced with this observational fact, Einstein was forced to abandon his cosmological constant. He later referred to the introduction of this constant, a mathematical term he inserted purely to preserve a preconceived notion about the universe's state, as his greatest mistake. The episode serves as a powerful testament to how deeply entrenched philosophical biases can, for a time, obscure even the most obvious scientific truths inherent in one's own equations. The universe, against centuries of human intuition, was revealed to be a dynamic, evolving entity. The dynamic nature of the universe leads us to the most extreme phenomena, predicted by general relativity, the singularity. Whether at the Big Bang or the core of a black hole, the singularity represents a point of infinite density and curvature, where the very structure of space-time collapses and the laws of physics cease to apply. The unpredictability inherent in the singularity poses a profound challenge to science. To deal with the singularities that arise from stellar collapse, Roger Penrose proposed the cosmic censorship hypothesis. This conjecture states that the singularity formed from the collapse of a star is always hidden from outside observers by an event horizon. The singularity is always cloaked, it is never naked. The philosophical and scientific importance of this hypothesis is immense. If a singularity were to become naked, directly visible to the external universe, without the protective shield of an event horizon, its point of infinite density and unpredictable nature would cause the predictability of the entire universe to break down. Since the universe is observed to follow predictable laws, this hypothesis suggests that the laws of nature conspire to ensure that all singularities remain hidden. While mathematicians like Hawking and others have found theoretical solutions to Einstein's equations that do allow for naked singularities, these solutions are typically highly specialized and unstable. The slightest perturbation or disturbance would cause the naked singularity to quickly cloak itself again behind an event horizon. Thus, the consensus in physics remains that, in any realistic cosmic scenario, the singularity is always hidden. This cloaking mechanism is critical to the black hole's other great paradox, the information paradox. When matter, which carries a massive amount of information, falls across the event horizon and into the singularity, that information is seemingly lost forever to the outside universe. According to general relativity, the black hole is simplified to only its mass and spin. As the saying goes, a black hole has no hair. All the complex details of the material that formed it are wiped clean. However, this loss of information fundamentally conflicts with the principles of quantum mechanics, which insist that information must be preserved. If information is truly lost, it violates the time reversal symmetry inherent in quantum laws. The discovery of Hawking radiation only deepened the paradox. This radiation, produced by quantum effects near the event horizon, causes the black hole to slowly evaporate. If the black hole eventually disappears entirely, the original information must somehow be released. Yet, Hawking radiation is purely thermal. It is random and carries no record of the specific information that fell in. The question is, if the black hole evaporates, where does the information go? This conflict, the inevitable collapse into a singularity versus the inviolability of information, highlights the limitations of our current partial theories. Neither general relativity nor quantum mechanics can fully describe this process. The black hole, therefore, serves as the ultimate theoretical laboratory, forcing physicists to search for the quantum theory of gravity that can finally resolve this fundamental paradox and provide a complete picture of the universe's dynamic evolution. The success in establishing the electroweak theory, which proved that the electromagnetic and weak nuclear forces are merely different aspects of a single unified force at high energies, fueled the ambition to incorporate the strong nuclear force into this framework. This effort is known as the Search for the Grand Unified Theory, or GUT. The basic idea of the GUT is profound. At an incredibly high energy level, far beyond anything achievable in current particle accelerators, the strong nuclear force, the weak nuclear force, and the electromagnetic force all become indistinguishable from one another. They merge into a single unified force. The forces we observe today are simply different aspects of this single underlying force that separated as the universe cooled. The energy required for this grand unification is estimated to be enormous, far exceeding the energy levels current accelerators can reach. Building an accelerator capable of reaching this unification energy would require it to be the size of the entire solar system, a task currently impossible. However, a scientific theory can be tested not only by replicating the conditions of its formation, but also by observing its consequences in the current universe. The Grand Unified Theory makes an extremely peculiar prediction about the stability of matter itself. It suggests that protons can decay. The proton, the basic unit of normal matter, which we traditionally consider to be stable, should, according to GUT, spontaneously decay into lighter particles, such as an anti-electron and other particles. This decay occurs because at the high energies necessary for unification, the fundamental particles inside the proton can sometimes briefly interact via the unified force and break down. The predicted lifetime for a proton is astronomically long, possibly a billion trillion years, a time span vastly longer than the age of the universe. To test this prediction, scientists cannot simply wait. They must observe a vast number of protons simultaneously in the hope of catching a rare decay event. Experiments, such as one conducted in a salt mine in Ohio using 8,000 tons of water, have diligently searched for this phenomenon. So far, however, no proton decay has been definitively detected. This negative result means that if proton decay does happen, the proton's lifetime must be even longer than initially predicted, forcing physicists to consider more complex GUT models. Beyond the proton decay test, the GUT is crucial to understanding the universe's most enduring enigma, the matter-antimatter asymmetry. According to the rules of quantum mechanics, the Big Bang should have created equal amounts of matter and antimatter. If this were true, they would have completely annihilated each other, leaving the universe filled only with energy, light, with no galaxies, stars, and/or planets. Yet we see a universe composed almost entirely of matter. The profound question is, where did the antimatter go? The answer lies in the subtle symmetries of nature. In the 1950s and 60s, a series of shocking discoveries revealed that the weak nuclear force does not respect certain symmetries. It was shown that the weak force breaks p symmetry, mirror symmetry, and CP symmetry, particle-antiparticle symmetry. This means the weak force does not treat a particle and its antiparticle the same way. This asymmetry is vital. It suggests that the antimatter universe would behave differently than our matter universe. If the GUT models can successfully incorporate this CP violation, they could explain how in the intensely hot, early moments after the Big Bang, a slight preference for matter over antimatter developed, leading to the matter that formed everything we see today. The breaking of CP symmetry also implies the breaking of T symmetry, time reversal symmetry, proving that time flows in an irreversible direction. The success of unifying the strong, weak, and electromagnetic forces, even if incomplete, highlights the central and singular remaining task for modern physics, the incorporation of gravity. The search for a quantum theory of gravity is the key to unlocking the universe's most fundamental mysteries, as it is the only way to reconcile the smooth space-time of general relativity with the probabilistic, quantized reality of the microscopic world. The clash between these two great pillars of 20th century physics is most acutely felt at the singularities of black holes and the Big Bang. Classical general relativity is incomplete because it predicts infinities at these points, telling us nothing about how the universe actually began or what happens inside the event horizon. The problem is that applying quantum principles to gravity leads to uncontrollable infinities. The perpetual creation and annihilation of virtual particles in the quantum vacuum result in infinite energy. According to general relativity, this infinite energy would create an infinite mass, which would warp space-time into an infinite curvature. Since we observe space to be finite and relatively smooth, this contradiction shows that both theories are incompatible at the most extreme levels. The path toward resolving this conflict led physicists to increasingly abstract concepts. One of the first major attempts was supergravity theory in the 1970s. This theory introduced the concept of supersymmetry, suggesting that every force-carrying particle must have a corresponding matter particle. This was an attempt to make the infinities cancel each other out. However, the mathematical calculations required to verify supergravity were so complex that no one was able to complete the proof and confirm its consistency. The next major attempt was string theory, which gained prominence in 1984. String theory proposes a radical shift. Elementary particles are not zero-dimensional points, but tiny one-dimensional strings. The different vibrations of these strings correspond to the different types of particles and forces we observe, including gravity. String theory successfully provides a quantum description of gravity that avoids the infinities because the interaction between two strings is spread out over a finite area, smoothing the quantum fluctuations. The major complication of string theory is that it is mathematically consistent only if spacetime possesses 10 or 26 dimensions, far more than the 4, 3 space 1 time we observe. The solution proposed is that the extra dimensions are compactified, curled up so tightly that they're too small to be observed. Further conceptual refinements in the 1990s led to the realization that different versions of string theory might simply be different approximations of a single, deeper, more fundamental theory, often called M-theory. Ultimately, the goal is singular: to find a theory so complete that it requires no arbitrary input, a theory that explains not only how the universe operates, but also why its laws and initial state are what they are. This final victory of human reason would be the key to answering the deepest questions of existence. The philosophical quest for the universe's ultimate fate rests on the behavior of gravity in its most intense form. We have seen that the general theory of relativity predicts the formation of singularities, points of infinite density and curvature where the fabric of space-time breaks down. These singularities are the inescapable endpoint of any gravitational collapse, whether it is the entire universe in a big crunch or a massive star collapsing into a black hole. The concept of the black hole was fully realized only with Einstein's theory. A star exhausts its nuclear fuel and can no longer generate the outward pressure needed to resist the inward pull of its own gravity. If its mass exceeds a certain limit, it is doomed to collapse past the neutron star stage, shrinking to a point of zero size but infinite density. The most fundamental feature of the black hole is the event horizon. This is the boundary from which the escape velocity exceeds the speed of light. Nothing that crosses this one-way membrane, not even light, can return. For an observer watching from a safe distance, the infalling object seems to freeze, fading out and turning red right at the edge of the event horizon. For the object itself, however, the experience is normal until it approaches the singularity. The singularity theorems, proven by Roger Penrose and Stephen Hawking, established that the formation of a singularity is an inescapable consequence of gravitational collapse. Inside the singularity is a point in the future of time for any matter that crosses the horizon. To maintain the predictability of the universe outside the black hole, Penrose proposed the cosmic censorship hypothesis. This conjecture states that the singularity must always be cloaked by the event horizon, never directly visible to the external universe. If a singularity were visible, a naked singularity, its unpredictable nature would cause the predictability of the entire universe to break down. While some theoretical solutions allow for naked singularities, they are highly unstable and would likely be hidden by the slightest disturbance. The singularity and the event horizon create the most profound conflict in physics, the information paradox. General relativity suggests that all information about the material that formed the black hole is lost inside the singularity. Quantum mechanics, however, insists that information can never be truly destroyed. The question of where the information goes remains one of the greatest unresolved challenges in combining gravity and quantum mechanics. The most astonishing discovery about black holes came in the 1970s, challenging the very definition of a black hole as an object from which nothing escapes. This conceptual breakthrough required the first true marriage of general relativity and quantum mechanics. In 1974, Stephen Hawking predicted that black holes are not entirely black. Due to quantum effects, they should slowly emit radiation. This process is now known as Hawking radiation. The core idea is based on the nature of empty space. According to quantum mechanics, empty space is never truly empty. It is filled with quantum fluctuations. These fluctuations constantly cause particle-antiparticle pairs to spontaneously pop into existence and immediately annihilate each other. When such a pair forms right at the edge of the event horizon, one particle might fall into the black hole while the other escapes. If the particle that falls in carries negative energy, it effectively reduces the black hole's mass. The escaping particle, carrying positive energy, is perceived as radiation emanating from the black hole. This radiation follows the exact pattern expected of a hot body, meaning the black hole behaves as if it has a temperature. This quantum result resolved the paradox related to entropy disorder. Since entropy must always increase and a black hole's area always increases when matter falls in, The black hole's area was thought to be a measure of its entropy. But anything with temperature must radiate. Hawking's radiation confirmed this, showing that black hole area and entropy are linked. The most shocking implication of Hawking radiation is that black holes are not immortal. Since they are continuously radiating energy, they must slowly evaporate. The smaller the black hole, the faster it radiates and the hotter it is. A black hole with the mass of the Sun has a temperature only a tiny fraction above absolute zero. It absorbs more energy from the cosmic microwave background than it emits. Such a black hole would take an unimaginably long time, 1 billion trillion 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 years, to fully evaporate. However, if tiny primordial black holes were formed in the extremely dense early universe, they would be much smaller than stellar black holes and would radiate much faster. If they had a specific small mass, they would have evaporated by now, ending their life in a final massive explosion. The search for these gamma ray bursts has been ongoing. The evaporation of black holes deepened the information paradox. If a black hole eventually disappears, the information that fell in must somehow be returned to the universe in the form of radiation. But the Hawking radiation is purely thermal and random, carrying no specific information. The question of where the information goes remains one of the greatest unresolved challenges in physics. This continuous conflict forces physicists to search for the ultimate quantum theory of gravity. The ascent toward a complete unified theory of physics leads to a profound philosophical dilemma concerning determinism and free will. As we have seen, the Newtonian worldview, formalized by Laplace, posited a strictly deterministic universe where the future of every particle, and thus every event, was entirely predictable if the current state were perfectly known. This view left no conceptual room for God's intervention after the initial creation, nor did it allow for genuine human free will. The first crack in this deterministic armour came with the problem of heat radiation in the 19th century. Scientists found that if a hot object radiated energy equally at all frequencies, the total energy radiated would be infinite. Max Planck solved this problem in 1900 by proposing the quantum hypothesis. Light and energy are emitted in small packets called quanta, which limited the total energy. However, the decisive blow to determinism was delivered in 1926 by Werner Heisenberg's uncertainty principle. This principle established a fundamental, unavoidable limitation on our ability to precisely measure both the position and velocity of a particle simultaneously. The act of measuring one property inevitably disturbs the other. The uncertainty principle meant that Laplace's vision of perfect prediction was impossible. If we cannot know the present state of the universe with perfect accuracy, then we cannot predict the future with perfect accuracy. This inherent randomness is not due to the limitations of our instruments, it is a fundamental feature of nature. Quantum mechanics replace definite outcomes with probabilities. An experiment yields multiple possible results, each with a specific probability of occurrence, and the dull exact outcome of a single event cannot be known beforehand. This led Albert Einstein to famously reject the idea that the universe operates on chance, stating God does not play dice with the universe. Yet experiments have repeatedly confirmed the validity of quantum mechanics and its inherent unpredictability. This inherent randomness in the universe complicates the search for a unified theory, and, more profoundly, it reopens the question of free will. If the universe were perfectly deterministic, our actions would merely be the inevitable consequence of a chain of events initiated billions of years ago. The question arises, if a complete unified theory exists that governs the entire universe, does it also determine the decisions we make? If the theory dictates every action, including our intellectual processes, can we truly trust the conclusions reached by our reason, since the theory might compel us to reach a wrong conclusion? One answer to this paradox lies in Darwin's principle of natural selection. Organisms that are better able to understand and react to their surrounding world are the ones most likely to survive. Organisms that draw incorrect conclusions about the world are driven to extinction. Throughout history, intelligence and scientific discovery have been powerful tools for survival. This pursuit of a unified theory is driven by the deepest human characteristic, curiosity. Since the dawn of civilization, humanity has refused to see events as purely random. The search for a complete description of the cosmos, to answer the questions of why we are here and where we came from, remains the highest goal of human civilization. The ultimate question is whether the discovery of a complete theory will fundamentally change human life. Science has already provided highly accurate theories that explain nearly everything except for the most extreme conditions. For practical purposes, even without a final theory, we have achieved extraordinary breakthroughs, such as nuclear energy and microelectronics, which came from the development of quantum mechanics and relativity. While the final theory might not directly affect our daily survival, the effort to find it is essential because it speaks to the core of what it means to be human. The relentless drive to know and understand the universe we inhabit. The deep structure of the universe is built upon fundamental units of matter and the forces that govern their interactions. Aristotle's belief that all matter was made of 4 elements, earth, air, fire and water, and 2 forces, gravity and levity, was a philosophical starting point. The modern discrete view of matter began with Greek philosophers who argued for small indivisible units called atoms. This was supported in 1803 by John Dalton, who showed that chemical compounds combine in fixed ratios. The final proof that matter consists of small units came in the 20th century when Einstein explained Brownian motion. However, atoms themselves were found to be divisible, composed of even smaller fundamental particles. Wolfgang Pauli established a crucial rule in 1925, the Pauli exclusion principle. It states that no 2 identical particles can occupy the same quantum state. This principle is vital. Without it, electrons would collapse into the nucleus, and all atoms would collapse, turning the entire universe into a dense soup. In 1928, Paul Dirac combined quantum mechanics and relativity, predicting that every particle must have an antimatter counterpart. This antimatter particle, the positron, anti-electron, was soon discovered. If a particle and its antiparticle meet, they annihilate each other in a flash of energy. The profound mystery remains. Why is antimatter so rare in the universe today, given that the Big Bang should have produced equal amounts? Modern physics holds that all forces are transmitted by the exchange of force-carrying particles, called bosons, between matter particles, like electrons and quarks. A matter particle emits a force particle, recoils, and the force particle travels to another matter particle, causing a push or pull. There are 4 fundamental forces in nature. Gravity. This is the weakest force, but it is dominant on large scales because it has an infinite range and is always attractive. It is carried by the hypothetical particle called the graviton. Electromagnetic force. This acts between charged particles and is transmitted by photons. It is vastly stronger than gravity and is essential for forming atoms and light. Weak nuclear force. This force is responsible for radioactivity. It acts on electrons and quarks and is carried by the W and Z bosons. Strong nuclear force. This is the strongest force, acting as the glue that holds protons and neutrons together to form the atomic nucleus. Its range is very small. The goal of physics is to unify all 4 forces into a single elegant equation. The first major success was the unification of the electromagnetic and weak forces into the electroweak theory. The next step is the search for the grand unified theory, GUT, which attempts to include the strong force. The final challenge remains incorporating gravity into this unified framework. The ultimate determination of the universe's fate depends on 2 crucial figures: the current rate of expansion and the average density of matter in the cosmos. The expansion rate tells us how fast the universe is pulling itself apart, and the density tells us how much gravity is pulling it back together. When scientists added up all the visible matter, all the stars, galaxies, and gas clouds that emit light, they found that this matter constituted only a tiny fraction of the necessary critical density required to halt the expansion. The visible matter alone suggested the universe would expand forever. However, observations of how galaxies rotate revealed a profound mystery. Galaxies spin so quickly that they should fly apart based on the gravitational pull of their visible stars alone. This suggested the existence of dark matter, a form of matter that does not emit or absorb light, making it completely invisible to telescopes, yet exerting a powerful gravitational pull. When scientists included the estimated mass of this dark matter, the total density of the universe still only amounted to about 1/10 of the mass needed to reverse the expansion. For decades, the standard cosmological model assumed the universe's expansion was decelerating, slowing down, due to the cumulative gravitational pull of all the matter. Then in the late 1990s, using distant observations, astronomers made a shocking discovery. The expansion of the universe is accelerating. It is not slowing down, it is speeding up. This acceleration requires a repulsive force that counteracts gravity on the largest scales. This unknown energy is now referred to as dark energy. Dark energy acts similarly to Einstein's cosmological constant, which he had earlier dismissed as his greatest blunder. But this dark energy is a reality, and it now dominates the universe's fate. The ultimate destiny of the cosmos is one of perpetual, increasing separation, where galaxies will eventually move so far apart that they will disappear from each other's view, leading to a universe that is cold, empty, and dark. The challenge for the final unified theory is now to explain the nature of this mysterious dark energy, which dictates the fate of all existence. We have reached the end of our brief history of time, a journey from the flat Earth resting on a turtle to the most complex ideas in physics, all in pursuit of a single coherent explanation for existence. The path has been defined by two fundamental questions. How does the universe behave, and why does it behave that way? The laws of science, as discovered by Galileo and Newton, confirm that the universe operates by fixed, rational rules, but the question of the initial state and the origin of the laws themselves remained open. General relativity demanded a beginning, the Big Bang singularity where predictability failed. Quantum mechanics introduced fundamental randomness, shattering the classical ideal of determinism. The ultimate theoretical synthesis, the search for the quantum theory of gravity, led to the most profound conceptual leap, the no-boundary proposal. This proposal suggests that the universe, described in imaginary time, is a self-contained finite structure without any boundary or edge. Imagine the surface of the Earth. It is finite, but if you travel on it, you never encounter an edge. Similarly, the universe, in imaginary time, would start smoothly at a point and expand without ever encountering a singular beginning or a boundary condition that needs to be arbitrarily set. Hawking's iconic formulation of this idea was, "The boundary condition of the universe is that it has no boundary." If this proposal is correct, it means the universe is a self-contained entity that simply is. It eliminates the need for an external creator to set the initial clock or choose the initial conditions. The philosophical implication is immense. If the universe is fully governed by an internal, self-consistent set of laws, and if these laws dictate that the universe simply is, then the logical necessity for a creator to intervene is removed. Hawking said that if the universe has no boundary, it would neither be created nor destroyed, it would simply be. The final victory will be in achieving a complete conceptual understanding of why the universe exists and why we are here to observe it. If we find the ultimate theory, it will not just be the victory of a few scientists, it will be the final victory of human reason, allowing us to finally grasp the complete, rational, and elegant set of rules that governs all reality. The singularity theorems establish that, according to general relativity, the universe must have begun with a Big Bang singularity. This point of infinite density is where the classical theory of gravity fails, signaling that the theory is incomplete. To go beyond this moment of failure, we must apply quantum mechanics to the universe's origin. The search for a quantum theory of gravity is essential to understanding the ultimate destiny of the universe. The early moments after the Big Bang can be described by known physics. The universe began in a state of extremely high temperature. As the universe expanded, its temperature dropped. When the size of the universe doubled, the temperature halved. At extremely high temperatures, collisions created particle-antiparticle pairs. About 1 second after the Big Bang, the temperature had dropped dramatically. At this stage, the universe was filled with fundamental particles. As the universe cooled further, some of these particles annihilated, leaving behind a small residual amount of matter. About 100 seconds after the Big Bang, the temperature had dropped enough for protons and neutrons to combine, forming hydrogen and helium nuclei. About 25% of the matter in the universe was converted into helium during this period. This prediction of primordial nuclear synthesis was made by George Gamow and Ralph Alpher in 1948. They also predicted that the remnants of these ancient reactions should still be detectable today as a cosmic radiation. The discovery of the cosmic microwave background in 1965 by Penzias and Wilson provided a major proof that the Big Bang model was correct. A million years after the Big Bang, The universe had cooled enough for electrons to combine with nuclei, forming atoms. Gravity began to slow the expansion in regions that were slightly denser than average. These denser regions collapsed to form galaxies and inside them stars. Large stars burned quickly and ended their lives in supernova explosions, creating heavier elements like carbon, oxygen, and iron. Our Sun, a second or third generation star, formed about 5 billion years ago. However, despite its success, the Big Bang model left 4 large unresolved questions. The uniformity problem. Why is the universe so uniform? The temperature of the microwave background is almost identical in all directions. Light could not have travelled from one side of the early universe to the other to synchronize their temperatures. The flatness problem. Why is the expansion rate so perfect? The required precision for the initial expansion rate is astonishing. The smoothness problem. Where did the seeds for galaxies and stars come from? The early universe was almost perfectly smooth. The small density fluctuations needed to initiate gravitational collapse are not explained. The hotness problem. Why was the universe initially so hot? To answer these questions, we must incorporate quantum mechanics into the universe's origin. The enduring philosophical question is why the fundamental constants of nature are precisely tuned to allow for the existence of life. The precise values of these constants seem to be a series of lucky coincidences. If the laws of physics were slightly different, the universe would be drastically different, and life as we know it would be impossible. The observation that the universe is perfectly calibrated for the existence of intelligent life is captured in the anthropic principle. This principle offers 2 main interpretations to explain the fine-tuning. The weak anthropic principle suggests that in a universe that is either very large or infinite, conditions suitable for life will necessarily arise in some regions. We, as conscious observers, are only able to exist and ask these questions because we happen to be in one of those regions. This interpretation argues that the laws might be random, but our observation is biased toward the regions where life is possible. The strong anthropic principle goes further, suggesting the existence of a multiverse, a vast number of separate universes, each with its own set of laws and physical constants. Only a small fraction of these universes would have laws that are suitable for the evolution of intelligent life. We exist in one of those special universes simply because we could not exist in any of the others. Hawking expressed philosophical unease with the strong anthropic principle. He found it difficult to accept that the entire universe, with its billions of galaxies, only exists for the sake of our limited ability to observe and think. Furthermore, science has historically rejected human-centered thinking. The anthropic principle, while thought-provoking, represents a potential defeat for science if it is used to explain away the fine-tuning as mere cosmic accident or luck. The hope remains that the final unified theory will prove that the constants of nature are not arbitrary at all, but are mathematically determined by the internal consistency of the theory itself. The scientific alternative to the anthropic principle is the inflationary theory, which provides a physical mechanism for solving the major problems of the Big Bang model. The failure of the standard Big Bang model to explain the uniformity and flatness of the universe, the problems that demanded an astonishing degree of fine-tuning in the initial state, pointed to a missing piece of physics. The universe appeared far too smooth and flat to have arisen from random initial conditions. This missing piece was provided by the inflationary theory, first proposed by Alan Guth in 1981. This theory suggests that the universe underwent an extremely short period of rapid, exponential expansion in the fraction of a second immediately following the Big Bang. During this period, the universe expanded at a rate far exceeding the speed of light. The mechanism driving this expansion involved the universe passing through a phase transition as it cooled. This transition released a tremendous amount of extra energy that acted as a repulsive anti-gravity force, causing space-time to inflate exponentially. The inflationary model provided elegant solutions to the core cosmological problems: the uniformity problem, horizon problem. Before inflation, the entire observable universe was a tiny region, small enough for light to travel across and synchronize its temperature. The exponential expansion then stretched this uniform, synchronized region across the vast distances we see today, explaining why the cosmic microwave background radiation is virtually the same temperature in all directions. The flatness problem. The enormous rapid expansion naturally drove the universe's geometry extremely close to the critical value needed to perfectly balance gravity and expansion. The universe was flattened by inflation, much like blowing up a tiny wrinkled balloon until its surface appears perfectly flat. The smoothness problem, the small density fluctuations needed to seed galaxies, are explained by the inherent quantum uncertainties that were present in the tiny pre-inflationary region. Inflation stretched these microscopic quantum fluctuations into macroscopic density variations that eventually grew into galaxies and clusters of galaxies. Inflation also provided a neat answer to the question of where the universe's vast number of particles came from. Hawking explains that the universe's total energy is zero. The matter particles have positive energy, but their mutual gravitational attraction creates an equal amount of negative gravitational energy. These two components cancel out. Thus, the universe could spontaneously create all its matter and energy from nothing, without violating the conservation of energy. As has been famously said, the universe is the ultimate free lunch. The success of the inflationary theory showed that a wide range of messy, non-uniform initial conditions could be smoothed into the well-structured cosmos we observe. This moved the discussion away from relying on the philosophical notion of fine-tuning and toward a scientific mechanism. Even the inflationary theory, for all its success, did still require a starting point, a field of energy to drive the initial expansion. This led Stephen Hawking and Jim Hartle to develop the no-boundary proposal, seeking to eliminate the need for any initial conditions, external forces, or boundary selections. This profound idea is rooted in the application of quantum mechanics to the entire universe, specifically through the mathematical concept of imaginary time. In imaginary time, time behaves like another dimension of space. This mathematical shift allows the universe to be modelled as a finite four-dimensional structure without any boundary or edge. Imagine the surface of the Earth. It is finite, but if you travel on it, you never encounter an edge or a wall. Similarly, the universe, when described using imaginary time, would start smoothly at a point, analogous to the North Pole, and expand without ever encountering a singular beginning or a boundary condition that needs to be arbitrarily set. Hawking's famous statement encapsulates this idea. The boundary condition of the universe is that it has no boundary. If this proposal is correct, it means the universe is a self-contained entity that simply is. It never began with a dramatic creation moment. The laws of quantum physics alone would dictate the universe's initial state, and it would be the one and only mathematically consistent state. The philosophical implication of the no-boundary proposal is immense. It suggests that the universe is logically and scientifically complete in and of itself. If the universe has no boundary or beginning, then the logical necessity for an external creator to set the initial clock or choose the starting conditions is removed. The debate then shifts from who created the universe and to who created the laws of physics. Even if the universe is self-creating, the question remains, why are the laws of quantum gravity so perfect and rational that they permit the existence of complex structures like ourselves? The ultimate victory of human reason would be achieved when we find the complete, unified theory that explains not only how the universe operates but also why its existence and its laws are inevitable. This knowledge, the answer to why we exist, would be the final shared achievement of all humanity. We have traversed the vast landscape of the cosmos, from the static Earth-centered models to the dynamic, quantum-fluctuating reality of the expanding universe. In all these models, the concept of time has been central yet elusive. Newtonian physics gave us absolute time. Einstein's special relativity introduced relative time, dependent on the observer's motion. And finally, quantum gravity introduced the strange spatial dimension of imaginary time. Yet, in our physical existence, time is undeniably linear and directional. In imaginary time, one can move forward and backward, much like moving in space. But in real time, the past and the future are fundamentally different. We possess memories of the past, but we have no knowledge of the future. Time seems to flow, and this flow is defined by the arrow of time. There are three distinct yet interconnected arrows that define this direction of time, and all three point in the same direction. The first is the thermodynamic arrow of time, the direction of time in which disorder, or entropy, increases. The second law of thermodynamics is the bedrock of this arrow. It states that the total entropy of a closed system must always increase. This law explains why we see events unfold in one direction, but never the reverse. A cup falls and shatters, increasing disorder, but the shattered pieces never spontaneously reassemble into a whole cup. The rising entropy implies the universe is moving from a state of high order to low order. The second is the psychological arrow of time, the direction in which we are able to remember the past but not the future. This arrow is fundamentally linked to the thermodynamic one. Memories are stored in our brains in an ordered state, but the process of recording a memory consumes energy, which leads to an increase in the total disorder, entropy, of the universe. We can only make memories in the direction of time in which entropy is increasing. The third is the cosmological arrow of time, the direction of time in which the universe is expanding rather than contracting. The crucial question is, why these three arrows are aligned? Why did the universe begin in a highly ordered state? The no-boundary proposal, derived from quantum gravity, suggests that the universe began in a remarkably smooth and ordered state. The small quantum fluctuations present at the beginning provided the non-uniformity necessary to seed the formation of galaxies and stars. This ordered beginning naturally explains why the thermodynamic arrow and the cosmological expansion arrow point in the same direction. The distinction between the past and the future, enforced by the arrows of time, faces its ultimate theoretical test in the concept of time travel, while the psychological and thermodynamic arrows make travel into the past an improbable reversal of nature. The equations of general relativity provide tantalizing, albeit highly unstable, mathematical loopholes that might allow such a journey. The first theoretical space-time model allowing travel into the past was found in 1949 by Kurt Gödel. Gödel's solution described a rotating universe where an astronaut could fly in a rocket ship and return to a point in time before they started their journey. Although observations show our universe is expanding, not rotating, Gödel's work established that time travel is theoretically compatible with the core framework of general relativity. Since then, other theoretical structures that create time loops have been identified, such as the space-time distortions near the interior of a black hole, or those potentially created by passing cosmic strings. While the twin paradox allows us to travel into the future by moving close to the speed of light, true travel into the past would require either surpassing the speed of light, which relativity forbids, or finding a shortcut through the cosmos.
This shortcut is the wormhole, or Einstein-Rosen bridge. A wormhole is a tunnel-like structure that connects two distant regions of space-time, allowing travellers to cover vast distances in a short period.
The major difficulty is that natural wormholes are highly unstable and would instantly collapse. To keep a wormhole open for travel, advanced civilizations would need to use matter with negative energy density. While this is forbidden by classical physics, quantum mechanics suggests it is possible on a small scale, a phenomenon confirmed by the Casimir effect. The possibility of travelling into the past through a wormhole inevitably leads to the logical nightmare of the grandfather paradox. If the past can be changed, fundamental contradictions arise. Two main theoretical resolutions exist for the paradox. The consistent histories approach. The past cannot be altered, and any attempt to change history is bound to fail. The alternative history hypothesis, multiverse theory. Travelling to the past causes a branching or split in history, creating a new, alternative timeline. Hawking's philosophical answer to these paradoxes is the chronology protection conjecture. This conjecture posits that the laws of physics conspire to prevent macroscopic time travel. The attempt to create a time loop, perhaps by stabilizing a wormhole, would cause the quantum vacuum to generate intense energy fluctuations. This energy would cause the region to collapse, preventing the time loop from ever fully forming. Hawking offered a simple practical argument. If time travel to the past were physically possible, we would already be witnessing a constant influx of visitors from the future. The absence of tourists suggests that the arrow of time we experience is a fundamental constraint of our physical reality. The journey through the cosmos reveals that the existence and fate of stars are governed by a delicate, profound balance between opposing forces. Every star's life cycle is a contest between the inward crushing force of gravity and the outward explosive pressure generated by nuclear fusion. A star begins its life as a cloud of gas, which gravity forces to contract and heat up until its core reaches the enormous temperatures required for hydrogen atoms to fuse and release energy. This energy creates a pressure that pushes outward, counteracting gravity and allowing the star to remain stable for billions of years. However, this stability is finite. When the nuclear fuel, the hydrogen, is exhausted, the star begins to cool and gravity inevitably takes over, forcing the star to collapse. The star's ultimate fate is determined entirely by its mass. The Indian physicist Subrahmanyan Chandrasekhar calculated the maximum mass a star can possess and still stabilize as a white dwarf. A white dwarf is an extremely dense object, stable because its electrons repel each other, a process governed by the Pauli exclusion principle of quantum physics. This limit is about 1.5 times the mass of the Sun. If the star's mass exceeds this limit, the electron pressure is not strong enough to stop the collapse, and the star continues to shrink dramatically. It may briefly stabilize as a neutron star, another incredibly dense object where gravity has compressed the electrons and protons into neutrons, held up by the neutron's own repulsive force. A neutron star, though only about 10 miles across, is almost as heavy as the Sun. But if the star's mass is even greater than the limit for a neutron star, nothing can stop the collapse. The star shrinks relentlessly, its density increasing until it reaches a point of infinite density and zero size. This is the formation of a singularity and the birth of a black hole. The star's immense gravity warps the surrounding spacetime so severely that light itself cannot escape, forming the event horizon. Everything, matter, light, and information, is trapped forever, leading to the singularity at the centre. This profound consequence of general relativity, the creation of an inescapable single point, is the inevitable endpoint for all massive stars. The black hole is the universe's ultimate gravitational prison. The ultimate philosophical ambition of physics is to arrive at the grand synthesis, a single unified theory that reconciles all 4 fundamental forces and all known physical phenomena. We have seen the partial success of unifying the strong, weak, and electromagnetic forces, but the crucial missing piece remains the quantum theory of gravity. The clash between general relativity, smooth, large scale, and quantum mechanics, discrete, small scale, is the greatest obstacle. General relativity predicts infinities at the singularity, a mathematical absurdity that shows both theories are incomplete. The search for the final theory led physicists to increasingly abstract concepts. Supergravity theory. Proposed in the 1970s, this theory introduced the concept of supersymmetry, suggesting that every force-carrying particle must have a corresponding matter particle. This was an attempt to make the infinities cancel each other out through the pairing of positive and negative infinities. However, the mathematical calculations were too complex to prove its consistency. String theory. Gained prominence in 1984, this theory proposed a radical shift. Elementary particles are not zero-dimensional points, but tiny one-dimensional strings. The different vibrations of these strings correspond to the different types of particles and forces, including gravity. String theory successfully provides a quantum description of gravity that avoids the infinities. The major complication of string theory is that it is mathematically consistent only if space-time possesses 10 or 26 dimensions, far more than the 4, 3 space 1 time, we observe. The theory suggests that the extra dimensions are compactified, curled up so tightly that they are too small to be observed. Further conceptual refinements led to the realization that different versions of string theory might simply be different approximations of a single, deeper, more fundamental theory, often called M-theory. The possibility of finding the ultimate theory raises questions about its complexity. If a complete theory is found, it will mean that we have discovered the complete set of rules that govern the universe, requiring no arbitrary parameters. The final victory will be in achieving a complete conceptual understanding of why the universe exists and why we are here to observe it. This knowledge should be shared with every ordinary person, not just scientists. The ultimate determination of the universe's fate depends on 2 crucial figures: the current rate of expansion and the average density of matter in the cosmos. The expansion rate tells us how fast the universe is pulling itself apart, and the density tells us how much gravity is pulling it back together. When scientists added up all the visible matter, all the stars, galaxies, and gas clouds that emit light, they found that this matter constituted only a tiny fraction of the necessary critical density required to halt the expansion. The visible matter alone suggested the universe would expand forever. However, observations of how galaxies rotate revealed a profound mystery. Galaxies spin so quickly that they should fly apart based on the gravitational pull of their visible stars alone. This suggested the existence of dark matter, a form of matter that does not emit or absorb light, making it completely invisible to telescopes, yet exerting a powerful gravitational pull. By measuring the rotation speeds of galaxies, we can infer the presence and amount of this unseen mass. When scientists included the estimated mass of this dark matter, the total density of the universe still only amounted to about 1/10 the mass needed to reverse the expansion. For decades, the standard cosmological model assumed the universe's expansion was decelerating, slowing down due to the cumulative gravitational pull of all the matter. Then, in the late 1990s, using distant observations, astronomers made a shocking discovery. The expansion of the universe is accelerating. It is not slowing down, it is speeding up. This acceleration requires a repulsive force that counteracts gravity on the largest scales. This unknown energy is now referred to as dark energy. Dark energy acts similarly to Einstein's cosmological constant, which he had earlier dismissed as his greatest mistake. But this dark energy is a reality, and it now dominates the universe's fate. The ultimate destiny of the cosmos is one of perpetual, increasing separation, where galaxies will eventually move so far apart that they will disappear from each other's view, leading to a universe that is cold, empty, and dark. The challenge for the final unified theory is now to explain the nature of this mysterious dark energy, which dictates the fate of all existence. We have reached the end of our brief history of time, a journey from the flat Earth resting on a turtle to the most complex ideas in physics, all in pursuit of a single, coherent explanation for existence. The path has been defined by two fundamental questions. How does the universe behave, and why does it behave that way? The laws of science, as discovered by Galileo and Newton, confirm that the universe operates by fixed, rational rules. But the question of the initial state and the origin of the laws themselves remained open. General relativity demanded a beginning, the Big Bang singularity, where predictability failed. Quantum mechanics introduced fundamental randomness, shattering the classical ideal of determinism. The ultimate theoretical synthesis, the search for the quantum theory of gravity, led to the most profound conceptual leap, the no-boundary proposal. This proposal suggests that the universe, described in imaginary time, is a self-contained, finite structure without any boundary or edge. Hawking's iconic formulation of this idea was, the boundary condition of the universe is that it has no boundary. If this proposal is correct, it means the universe is a self-contained entity that simply is. It eliminates the need for an external creator to set the initial clock or choose the initial conditions. Hawking said that if the universe has no boundary, it would neither be created nor destroyed, it would simply be. The final victory will be in achieving a complete conceptual understanding of why the universe exists and why we are here to observe it. If we find the ultimate theory, it will not just be the victory of a few scientists, it will be the final victory of human reason, allowing us to finally grasp the complete, rational and elegant set of rules that governs all reality.